Today we're diving deep into Kimi K2.5, a groundbreaking open-source multimodal model from Moonshot AI. This isn't just another large language model, it's a trillion-parameter mixture of experts architecture with 32 billion activated parameters per forward pass, trained on 15 trillion tokens. What makes K2.5 truly special are two fundamental innovations that we'll explore in detail. First, joint optimization of text and vision that enhances both modalities simultaneously, and second, Agent Swarm, a framework for parallel agent orchestration that reduces inference latency by up to 4.5x. By open-sourcing their post-train checkpoints, Moonshot is accelerating the entire field's progress toward general agentic intelligence. Conventional wisdom and multimodal AI suggests introducing vision tokens predominantly in the later stages of language model training, typically at ratios of 50% or higher. The reasoning seems intuitive: establish strong linguistic competence first, then rapidly acquire multimodal capabilities as a post-hoc addition. But this approach forces a fundamental trade-off. With a fixed total token budget, aggressive late-stage vision training often compromises either linguistic or visual capabilities. You're essentially asking the model to forget some of what it learned about language to make room for vision. The K2.5 team discovered something counterintuitive through careful ablation studies. Given a fixed vision text token budget, early fusion with a lower vision ratio actually yields better results than late fusion with higher ratios. Look at these numbers: early injection at 10% vision ratio outperforms late injection at 50% across vision knowledge, vision reasoning, OCR, text knowledge, and coding benchmarks. The key insight? Extended co-optimization at moderate vision ratios allows the model to naturally develop balanced multimodal representations. Rather than treating vision as an add-on, K2.5 mixes text and vision tokens at a constant ratio throughout the entire training process. At the heart of K2.5's visual processing is Moonshot 3D, a native resolution vision encoder that eliminates the need for complex image splitting and splicing operations. Initialized from SIG-LIP SO 400M, it incorporates the NavIT packing strategy where images are divided into patches, flattened, and concatenated into one-dimensional sequences. This enables efficient training on images at varying resolutions. For video understanding, Moonshot 3D extends this philosophy to the temporal dimension. Up to 4 consecutive frames are treated as a spatiotemporal volume, jointly flattened and packed. Lightweight temporal pooling then aggregates patches within each chunk, achieving 4x temporal compression. This means K2.5 can process videos up to 4 times longer within the same context window while maintaining full weight sharing between image and video encoders. Here's a fascinating cold start problem. Pre-trained vision language models don't naturally perform vision-based tool calling. Conventional approaches address this with manually annotated chain-of-thought data, but such methods are limited in diversity, often restricted to simple diagrams and primitive operations like crop, rotate, and flip. K2.5 introduces a novel approach called Zero Vision SFT, using only text-supervised fine-tuning data to activate visual agentic capabilities. All image manipulations are proxied through programmatic IPython operations, serving as a generalization of traditional vision tool use. This enables diverse reasoning behaviors including pixel-level operations like object counting via binarization. The remarkable finding? Because joint pre-training already establishes strong vision-text alignment, capabilities generalize naturally across modalities. When training visual reinforcement learning, you might expect a trade-off with text performance. The K2.5 team found the opposite. Outcome-based visual RL produced measurable improvements in text benchmarks. MMLUPro jumped from 84.7% to 86.4%, GPQA Diamond from 84.3% to 86.4%, and Longbench V2 from 56.7% to 58.9%. Analysis suggests visual RL enhances calibration in areas requiring structured information extraction, reducing uncertainty on queries that resemble visually grounded reasoning. This bidirectional enhancement, where text bootstraps vision and vision refines text, represents a new paradigm of cross-modal alignment. K2.5's joint multimodal RL organizes domains by abilities like knowledge, reasoning, and coding, not by input modality. Most existing agentic systems rely on sequential execution of reasoning and tool calling steps. While this works for simpler tasks, it becomes increasingly inadequate as complexity grows. Even models capable of hundreds of reasoning steps suffer from linear scaling of inference time, leading to unacceptable latency for real-world applications. As agentic workloads expand to include massive-scale research, design, and development tasks with broad information gathering and multi-branch reasoning, the sequential paradigm encounters significant bottlenecks. The limited capacity of a single agent working through each step one by one can exhaust practical reasoning depth and tool call budgets. To overcome these limitations, K2.5 introduces agent swarm and parallel agent reinforcement learning, or PRL. Instead of executing tasks as a reasoning chain, K2.5 initiates an agent swarm through dynamic task decomposition, subagent instantiation, and parallel subtask scheduling. The architecture is deliberately decoupled. A trainable orchestrator coordinates frozen subagents instantiated from fixed intermediate policy checkpoints. This design avoids end-to-end co-optimization to circumvent two fundamental challenges: credit assignment ambiguity and training instability. By treating subagent outputs as environmental observations rather than differentiable decision points, the orchestrator can focus purely on high-level coordination logic while disentangling it from low-level execution proficiency. Training a reliable parallel orchestrator is challenging due to delayed, sparse, and non-stationary feedback. The PRL reward function addresses this with three components. R_parallel incentivizes subagent instantiation to prevent serial collapse, where the orchestrator defaults to single-agent execution. R_finish rewards completed subtasks to prevent spurious parallelism, a reward hacking behavior where the orchestrator spawns many subagents without meaningful task decomposition. And R_performance evaluates overall solution quality. The hyperparameters lambda_1 and lambda_2 are annealed to 0 over training, ensuring the final policy optimizes for the primary task objective. The team also introduces critical steps as a metric, analogous to the critical path in a computation graph, to measure actual parallel efficiency. Token efficiency is central to models with test time scaling. While imposing budget constraints effectively limits inference time compute, the team observed a length overfitting phenomenon. Models trained under rigid constraints fail to generalize to higher compute scales. They can't leverage additional tokens to solve complex problems. Enter toggle, a training heuristic that alternates between inference time scaling and budget-constrained optimization. In phase 0, the model trains to solve problems within a task-dependent token budget, but only when mean accuracy exceeds a threshold. In phase 1, the model generates responses up to the maximum token limit. This stochastic alternating optimization reconciles reasoning capabilities with computational efficiency, achieving 25 to 30% fewer output tokens with negligible performance impact. Let's look at the numbers. On AIME 2025, K2.5 achieves 96.1%, approaching GPT-5.2's perfect score while outperforming Claude Opus 4.5's 92.8%. On Humanity's last exam with tool use, K2.5 scores 50.2%, beating Gemini 3 Pro's 45.8% and GPT-5.2's 45.5%. For software engineering, K2.5 reaches 76.8% on SWE Bench Verified. In video understanding, it sets new state-of-the-art records, 86.6% on Video MMMU, 75.9% on LV Bench. For computer use, K2.5 achieves 63.3% on OS World Verified, approaching Claude Opus 4.5's 66.3%. Perhaps most impressively, on the challenging BrowseComp benchmark for deep research, K2.5 scores 60.6% single agent, substantially outperforming Claude Opus 4.5's 37% and Gemini 3 Pro's 37.8%. Agent Swarm transforms K2.5's already strong agentic capabilities. On BrowseComp, it jumps from 60.6% to 78.4%, an absolute gain of 17.8 points, even surpassing GPT-5.2 Pro's 77.9%. On WideSearch, item F1 improves from 72.7% to 79%, outperforming Claude Opus 4.5's 76.2%. The efficiency gains are dramatic. Execution time reduces by 3x to 4.5x compared to single-agent baselines. As target F1 increases, single-agent execution time grows linearly, while Agent Swarm maintains near-constant low latency. Beyond raw performance, Agent Swarm functions as proactive context management. Rather than reactively truncating or discarding context, it decomposes tasks into parallel, semantically isolated subtasks, each with bounded local context. Only task-relevant outputs flow back to the orchestrator, context sharding instead of context truncation. Kimi K2.5 demonstrates that scalable, general agentic intelligence is achievable through two complementary innovations: joint optimization of text and vision that achieves bidirectional enhancement, and agent swarm that transforms sequential tool execution into parallel processing. The unified architecture integrates vision and language, thinking in instant modes, chats and agents. By open-sourcing their post-trained checkpoints, Moonshot AI is enabling the research community to explore, refine, and deploy these capabilities. This represents a significant step toward the goal of general agentic intelligence systems that can reason, perceive, and act across modalities and tasks with human-level flexibility.